February 1940, trial order issued, 1 grenade pin removed, condensation logged in the line, clearance delayed, failure noted, inspection stamp missing on the cylinder. Report sealed that night. Early 1940 exposed merchant shipping to air attack. Coastal convoys carried food, fuel and raw metals. German aircraft exploited predictable routes and timings. Low-level bombing increased hit probability on decks. Torpedo aircraft required straight, steady approach lines. Escort coverage was uneven along the British coast. Fighter protection rarely matched convoy schedules. Standard anti-aircraft guns were in short supply. Many merchants sailed with minimal defensive mounts. Admiralty staff faced immediate losses and political pressure. Stopgap weapons became acceptable procurement solutions. The desired outcome was disruption, so not reliable destruction. A low-cost device had to fit quickly. Deck structure limits ruled out heavy recoil systems. Training time for merchant crews stayed limited. Ammunition supply had to use existing stocks. Industrial capacity outside ordnance factories was necessary. Cornish firms offered valve and compressor experience. Holman Brothers produced pneumatic equipment and tools. Their skill set matched pressure system fabrication. They proposed a pneumatic mortar for ship defense. The concept avoided cordite and recoil loads. Compressed air could replace propellant in emergencies. Steam power was also available on many craft. The device became known as the Holman Projector. Its role was defensive coverage for merchantmen. It was intended for low-altitude attack profiles. The Luftwaffe often attacked ships at low height. And those profiles supported a short-range upward burst. The system also supported convoy routes later supplying USSR. Northern convoys faced aircraft from Norway bases. Any deterrent effect mattered on long routes. Procurement files prioritized quantity over precision. Cost and speed outweighed ballistic performance. Risk acceptance was institutional during early war. That environment produced unconventional naval weapons. Holman became one of those expedients. Its appearance was ordinary compared with naval guns. Its danger came from fuse and fragments. Its value came from uncertainty imposed on pilots. Ship defense doctrine adapted to imperfect tools. This device aimed to alter attack geometry. A forced climb reduced bombing accuracy. That was the practical intent in memos. Holman Brothers sought wartime contracts for relevance. So Trev Holman supported the initial Admiralty approach. Engineer Maurice Oram led design and trials. Early sketches borrowed Stokes mortar concepts. A smooth bore tube reduced machining requirements. A pressure chamber replaced the cartridge case. A simple base handled thrust into the deck. Initial tests used inert weights for safety. Reports described an 18-pound weight thrown far. Those tests proved the pressure pulse concept. They did not prove anti-aircraft accuracy. Admiralty officials requested a formal demonstration. A February 1940 trial was organised quickly. The trial emphasised rate of fire and simplicity. Results were accepted as adequate for stopgap use. Large early orders followed for merchant fitting. Figures around 1,000 appear in summaries. Production was spread across local suppliers. Cast iron parts reduced demand for scarce alloys. Mild steel tube stock served as barrels. Valve bodies required consistent machining tolerances. Pressure fittings needed inspection and stamping. Air bottle supply required certified cylinders. Holman's already worked within pressure regulations. That reduced development risk for Admiralty buyers. Complex sights were excluded from the baseline. Some mounts used improvised ring and post sights. Designers accepted deliberately limited aiming capability. They focused on producing a disruptive screen. Multiple models were developed under changing needs. Mark I prioritized compressed air operation. Mark II was requested for steam operation. Steam trawlers lacked air bottle refilling logistics. Salt weather caused rapid corrosion of air valves. Condensation created failures in early steam attempts. A Mark II added a firing trigger for control. A later Mark III improved loading and sealing. Some reports cite salvo capability in Mark III. Planned Mark IV concepts remained on paper. By then, better weapons were becoming available. Manufacturing still faced steel and labour constraints. Skilled fitters were diverted to other programs. Holman assembly steps were kept intentionally simple. Parts were designed for quick replacement afloat. Documentation remained brief for merchant crews. 2 operators were usually assigned in drills. 1 handled ammunition preparation and loading. 1 controlled elevation and firing controls. That division reduced overall mishandling probability. It also imposed manpower cost on the small crews. The projector entered service during heavy losses. Its adoption reflected scarcity more than confidence. So that tension appears in later evaluation notes. Procurement still continued through late 1941. Stopgap value was judged greater than risk. Development choices always tracked supply constraints. The Holman Projector functioned as a gas mortar. Energy came from compressed air or high-pressure steam. The barrel was unrifled and smooth internally. Barrel length is often given near 4 feet. Some accounts state roughly 4.5 feet. A muzzle-loaded projectile dropped into the tube. Mark I used a Stokes-style drop-firing system. The round struck the base to trigger discharge. A valve opened to release a pressure pulse. That pulse expanded behind the projectile canister. The canister acted as a sabot and holder. It centered the grenade inside the tube. It restrained the grenade lever during launch. Though the explosive payload was a Mills bomb grenade, the pin was removed before insertion into canister. A time delay fuse initiated after lever release. For projector use, a shorter delay was reported. Some descriptions cite about 3.5 seconds. A short fuse aimed for an airburst above the ship. Fragmentation was expected to damage low aircraft. Explosion energy was small compared with shells. A Mills bomb held a few ounces of explosive. Lethality depended on fragment density in the air. Ceiling height limited the fragment pattern usefulness. Mark I trials reported heights around 600 feet. Mark III trials reported heights near 1,000 feet. Those values describe peak height, not accurate range. Exit velocity remained modest because barrel was short. Modest velocity increased wind sensitivity immediately. Ship roll altered elevation between shots. Crosswind drift was difficult to estimate. No stabilization system existed in the smooth bore. The canister had limited aerodynamic correction. Therefore, aiming was approximate by necessity. Operators fired patterns rather than precision leads. Pressure supply for Mark I used air bottles. High-pressure bottles fed regulators and hoses. Hose integrity became a maintenance issue at sea. Leaks reduced height and increased misfire risk. Bottle capacity limited sustained firing duration. Some accounts describe about 50 shots per bottle. Placing bottles required clamps and careful handling. Cylinder valves could freeze in cold conditions. Gauge errors could mislead pressure management. Low pressure caused short lofting trajectories. Short lofting increased shrapnel hazard to crew. As a critical hazard was grenade backfall onto deck. Backfall could occur with weak pressure pulses. Backfall could also occur with barrel obstructions. Crew instructions emphasized immediate cover after firing. Cover reduced injury from descending fragments. Cover also reduced sustained tracking of aircraft. Mark II steam's operation changed the internal system. Steam supply came from ship boiler connections. Steam pressure varied with engine load demands. Low load reduced available launch pressure. Condensation formed water inside cooler pipe runs. Water reduced effective pressure during discharge. Water also created inconsistent firing behavior. Mark II replaced drop firing with a trigger system. The trigger allowed venting condensate before firing. Drain points were added in some installations. Valves still suffered from rust and scale. Her steam leaks created those scalding hazards for operators. Steam fittings required survey approval on merchants. Mounts were designed for minimal recoil transmission. Recoil was light compared with gun systems that allowed installation on small trawler decks. Traverse was usually manual with a simple pivot. Elevation was adjusted by hand levers or wedges. Sights were crude and sometimes locally fabricated. No fire control predictors were integrated. No radar or power drive interfaced with the mount. The projector was therefore a manual point device. Loading procedures carried significant safety risk. Removing the grenade pin was irreversible. Once released, the fuse continued burning. Canister integrity was essential for lever restraint. Damaged canisters could release levers prematurely. Premature release could detonate on deck. Tin canisters could deform under rough handling. Deformation could jam the canister in the barrel. A jam created a blocked tube under attack. Clearing a jam required venting pressure first. Vent valves were not always well placed. Improvised venting procedures developed by each crew. Salt spray contaminated moving valve surfaces. Lubricants had to remain stable with steam. Incorrect lubricants caused sticking and partial opens. Partial opens produced unpredictable projectile height. Fuses also behave differently under cold soak. Low temperature can delay chemical burn rates. Delayed bursts could occur above friendly deck. Shortened delays could burst near the muzzle. Either variation increased operator risk materially. Reports describe crews diving for cover routinely. Some notes describe shrapnel falling onto deck planks. Wooden decks could splinter under fragment impacts. Canvas covers could ignite from hot fragments. Local modifications added splinter screens and sandbags. Such additions were not standardized across ships. Non-standard changes complicated formal evaluation. Accuracy limits were structural, not merely training. The device was never a true anti-aircraft gun. It was a pressure launcher for airborne bursts. Its engineering merit was low material demand. Its engineering weakness was safety margin thinness. Testing addressed feasibility more than reliability. Field conditions revealed condensation and corrosion issues. Those issues drove continual minor redesign attempts. Even improved marks could not fix ballistic limits. That limitation framed later procurement choices. The projector was issued mainly to merchant ships, and it appeared on defensively equipped merchant vessels. Some convoy inventories list Holman among armament. Atlantic convoys faced aircraft and U-boat combined threats. Air attacks often began with low reconnaissance passes. When aircraft committed, Holman crews were ordered to fire. Firing arcs were chosen to avoid rigging and lifeboats. Mount position depended on steamline routing. Air bottle stowage also constrained installation location. Ammunition lockers were placed near the mount. During alerts, canisters were assembled in advance. Pins were removed only on direct command. The loader inserted the grenade into canister carefully. The canister was loaded muzzle first into tube. Mark I could discharge automatically on base impact. Mark II required trigger actuation after seating. After firing, the crew sought immediate cover. Cover reduced injuries from falling fragments. The elevation operator adjusted angle between shots. Patterns were fired to create a burst screen. Timing aimed to burst near low-flying aircraft. Real timing errors were large at closing speeds. Most bursts occurred behind the aircraft line. Behind bursts could still influence pilot behavior. Pilots could assume heavier flak present nearby. Some after-action notes describe aircraft turning away. Other reports show attacks continuing without deviation. Direct hits were rare because aiming was approximate. Occasional damage claims describe aircraft hit by fragments. Verification was difficult during convoy conditions. Smoke, spray, and movement obscured observation. Night attacks reduced visibility for damage assessment. The projector could be used in darkness, and its flash could also reveal ship position. Some captains limited use during submarine risk periods. Other captains prioritized air deterrence above concealment. In low-altitude torpedo runs, deterrence mattered most. A pilot forced higher reduced torpedo aiming accuracy. That tactical logic matched Admiralty intent statements. In northern waters, low attacks also occurred. Arctic convoys carried supplies for Soviet resistance. Air threat came from Norwegian coastal airfields. Merchant ships still relied on mixed defensive kits. Holman units were present during early convoy phases. Later, improved guns reduced reliance on projectors. Training on merchant decks remained basic and brief. Misfire drills were critical during live alerts. A misfire left a live grenade in the tube. Extraction required venting and careful handling. And some crews reported fear of this condition. Fear reduced willingness to fire under pressure. Some crews still fired to create smoke bursts. Smoke aloft could obscure an attacker's view. Smoke also obscured friendly gunners intermittently. Coordination across merchant crews was inconsistent. Some ships fired early and wasted ammunition. Other ships withheld fire until too late. Admiralty analysts noted inconsistent employment patterns. Logistics teams tracked grenade availability carefully. Grenades also served boarding defense needs. Army demand competed for grenade stocks. Supply limits reduced projector firing opportunities. Some crews used the projector for signaling or recreation. Those uses did not reflect combat doctrine. Combat doctrine remained focused on low-altitude disruption. The projector could not stop a determined attack. That it could raise uncertainty in approach planning. That uncertainty was its operational contribution. Institutional reports treated deterrence as measurable effect. Pilots reacting to bursts changed attack geometry. Changed geometry reduced bomb or torpedo accuracy. Such outcomes were reported without precise attribution. Crew confidence was also recorded in naval paperwork. Some crews valued any visible defensive action. Other crews distrusted the projector as unsafe. Safety reports mention fragment fall onto firing decks. Some notes mention grenades failing to clear the ship. That possibility created reluctance in operators. Reluctance reduced firing rates during attacks. Admiralty memos compared hazard against available alternatives. Where no guns existed, Holman was still fitted. Where guns arrived, Holman was removed or neglected. Enemy intelligence reaction is hard to document. However, pilot caution toward flak was routine. A perceived barrage could still influence decisions. Black smoke bursts increased perceived flak density. Multiple bursts created a false heavy weapon impression. This effect was noted in some service accounts. Strategically, the device bought time for industry. It covered gaps until Oerlikon deliveries increased. It reduced pressure on scarce gun mount allocations. Procurement officers could equip many ships rapidly. That scaled defense faster than gun production. The Soviet supply mission increased urgency of scaling. Even marginal deterrence reduced expected losses. Marginal reduction mattered across many sailings. Command evaluations remained mixed and cautious. The weapon was never credited as decisive. And it was credited as a temporary expedient. That judgment guided subsequent cancellation decisions. Psychological impact existed in report language only. Strategic impact existed in allocation flexibility. Those two impacts explain continued short-term use. By late 1941, better AA weapons spread. Oerlikon cannons and improved mounts reached merchants. Training programs matured for DEMS crews. Holman limitations became clearer during repeated action. Operator hazard remained higher than acceptable. Maintenance burden remained high in salt conditions. Steam variations remained inconsistent under engine load. Procurement shifted towards standardized gun systems. Dockyard time still delayed removal on some ships. Some projectors stayed due to refit backlogs. Later, many were removed as routine modernization. The post-war reviews framed ASID as emergency improvisation. Museums retain examples for industrial history. Surviving canisters show the grenade-based logic. The device illustrates bureaucratic risk acceptance. It also illustrates British pressure technology repurposing. Its battlefield record shows limited confirmed damage. Its deterrence effect remained difficult to quantify. Its legacy is largely procedural, not tactical. It occupied a gap until real guns arrived. For convoy defense, it served as false flak. For crews, it imposed strict handling discipline. For procurement, it delivered rapid mass fitting. For pilots, it created uncertain burst risk. The Holman Projector scared Luftwaffe pilots anyway.